Okay, so in this talk, I'm going to focus on two instances of the same big picture mathematics question, which is suppose I have a group and I take the orbit of the point, and I want to count points in that orbit, and then I have some cutoff condition, which is useful for whatever it is. How can I do that? So the first problem we're going to look at is the so-called Gauss circle problem, and this is going to act as a bit of a warm-up. And historically, it's kind of the inspiration for some of the methods that got developed later. It's a nice warm-up for us to start with. And then I'm going to present the second of these classical problems. It's the Apollonian counting problem or Kleinian counting problem, which is every talk has to count the Gauss constants. Now, before I actually solve or tell you how to put this counting problem, we're going to take a little detour into spectral theory of hydrology. We're going to try and keep this as brief as possible and avoid technical details. What do you mean by the hydrology? Okay, good. After that, we're going to have another little warm-up, but now we're going to have a hyperbolic warm-up, a hyperbolic spectrum. And then finally, I'll show you how to code this Apollonian. We're going to take some detours, but hopefully it makes sense. Okay, let's start with our warm-up. So here's the manual stuff. In 1834, Gauss made some progress in the following topic. He wants to count the number of lattice points in the integer lattice inside a circle of radius. So to put this another way, here's the mathematical formula. So he wants to count these lattice points inside of t squared, such that x squared plus y squared equals 2. Just to kind of emphasize my point. Oh, and he found that there's a main term, pi r squared, the area of a circle. That's not that surprising. And then there's an error term, which is able to upper bound by constant quantity. Just to emphasize my point, here my group is t squared, and the point that we're going to take the orbit of is the origin. So here we have the orbit at the point, in orbit, which satisfy this inequality given by this. Just a restatement. So let's go over Gauss's root because it's very nice. So the question is, here is my circle of radius r, and here is my integer lattice. How many lattice points lie inside of the circle of radius? And what he's going to do is he's going to place each lattice point inside of the box. And if the box is entirely contained in the circle, then we color it blue, or I color it blue. And if it's intersecting the boundary of the circle, then we color it red. And your true count is lower bounded by the blue box, and it's upper bounded by the blue plus the red box. And now if you want to estimate those two quantities, you just place them in a circle on the outside, and you can calculate how wide this strip is, and we know that the circumference of the circle is 2 pi r. And so that gives you your error term, which is proportional to the circumference of the circle.
You get the constant. Oh, big O.
Big O means less than or equal to constant times radius.
And constant, you know, from the 2r.
It's 2r, but then there's also a factor of like 1 over root 2 that comes from all different radius.
You know the constant.
You know the constant, so you can actually get a. And he conjectured that the true error term should be about sine square root of all. Okay, so what progress have we made since then?
So what year is that?
1834.
Oh, good.
Yeah. So today we have a lower bound on this exponent, which is 1.5, and we have an upper bound, which is 0.6274. The lower bound comes independently from Hardy and Landau. I think also Baranoy works on this. And the upper bound is quite recent, it's 2007. There's still a lot of progress to be made on this question. The upper bound is by Borgan and uses some L function machinery, which I don't want to get into, so we're going to ignore that for the time being and focus a little bit more on Huxley's bound of 2000, which you can see is almost in the third decimal place, and we're off by about 0.1, so we're really taking small steps. It's purely empirical. I've seen. You can describe a random process where the point inside of the box is sort of randomly distributed on either side. Yeah, and the probability that it's inside or outside, and then the error term on that should be about square root of. Okay. And so is this statement of the error just for large R, or? Yeah, just for large. This is, throughout the talk, I'm really talking about asymptotics. Okay, now I want to focus a little bit on Hardy and Landau and Huxley's proof, which uses the trick by Van Forthet, which involves cross-functioning. So, for anyone who doesn't know what that is, cross-transformation is the central rule in number theory. It says the following: if I have a smooth C2 function, and I want to sum it over the integers, then I can also sum the Fourier transform over these two sum for this is a kind of bread and butter theorem for analytic number theorists, and it inspired my favorite quote, which is by Apollonian. It says the exponential function violin of the mathematical orchestra. The sawtooth is the flute. Themes are developed by violins. And the cross-constellation formula is very deep. I don't really know what the first part means. So with that, we can try and understand how to make progress on the Gauss circle problem. And the way you do that is our true count. We're just going to define in terms of the sum. So it's the sum over points in the integer values of an indicator function that says you're inside of this. Right? I'm not doing anything dramatic here. Now, if we want to use Poisson summation, we need our function to be smooth. So we're going to smooth it. And the typical way you do that is just involve with some smooth function as some active epsilon you play with. And now my true count is upper and lower bounded by this epsilon. Okay. So now we have a sum over smooth functions, and we can apply the Poisson summation formula. Okay, don't be scared that I've moved up the dimension. This is generalized two-dimensional Fourier transform. So I take the Fourier transform. The Fourier transform of a convolution is the product of the Fourier transforms. And then my main term is just going to come from the zero Fourier coefficient. And then the whole game is we have a sum of some Fourier coefficients. You have some exponentials in there. So you can use Fourier analysis, you can use our understanding of exponential sums to try and bound what you think. This talk isn't really about this. The second part is more about moving to frequency space. aspect of this problem. Okay. So with that, let's move to our second classical problem for the top. And the problem is it's inspired by the guy Apollonian. Perga is in modern day Turkey. At the time, it was part of the Greek islands. You might know him from his books on sections, and parabolas, and hyperbolas. So he was really interested in things like tangents and points. He has all these little calculations on that. And one of the theorems that he came up with is the following. If I have three mutually tangent circles, so here C1, C2, and C3, these are all mutually tangent, then there exist two additional circles, C0 and C4, which are tangent to the original. It's kind of obvious when you draw the picture, but it's not obvious that this is always the case. By the way, for this talk, I have straight lines with infinite radius. So those are the Greeks.
The projected geometry aspect of forms, it's actually that looks like an ellipse to me.
That might be a byproduct of my drawing.
I think it was architecture.
So now we skip forward 1800 years, and René Descartes, in a letter to Princess Elizabeth of Bohemia, states the next theorem in this line. And for this, I'm going to define the bend, which is the sine inverse radius of a circle. So the inverse radius is one of the radius. This outer circle has negative bend because its interior is like we flip the interior, so it has negative bend.
That's what we call curvature.
Well, I want to use the word bend because in higher dimensions, I always want to use 1 over the radius, not 1 over the radius. So the definitions agree in dimension 2, but in higher dimensions,
You say principal curvature.
is it principal curvature? Okay. Really, I'd say bend because so Descartes has the following theorem, which is how do you find the radius of a circle C4? Well, the theorem is that 2 times the sum of the bends squared is equal to the sum of the bends all squared. Obviously, this is a quadratic equation, so we need 2 solutions. That's why we get these circles. Now next, also in the 17th century,
Who is the woman? Oh, there was
Princess Elizabeth of Bohemia. Apparently, she was a student of Descartes, whom he found rather annoying, and set these geometric problems to try and get her off that. Enthusiastic.
He later thought Queen Christina of Sweden.
Yeah, this is
A lot of people.
book of letters to European princes. So now we jump forward a little bit. And Leibniz takes the same idea for the partial configurations. And he plays around with the idea of continuing this process. So here I have 4 circles in a Descartes configuration. And you can still take any 3 of these circles and find more tangents. You can fill in the gaps. And then you can continue to fill in the gaps, and you can continue ad infinitum. It's worth noting that this is, a notion of fractals that comes well before Serpentian triangles, all of these foundation of the study of fractals really dates back a little bit further. Okay, the next person in this story, there's a lot of fancy is the Nobel Prize winning chemist, Frederick Stony. So he won his Nobel Prize for radioactive decay, and the idea that radioactive decay is the nucleus shedding particle. But after you win your Nobel Prize, and you can do whatever you want. In particular, you can publish poems in Nature. And he has this poem where he rederives Descartes' formula. And he also shows that there exists an infinite pattern where all of the bands in the number of radii are integers. So now the number theorists get involved, because now you have a quadratic form and you have integer solution of a quadratic form. So that's quite nice.
I think that's what really.
Excuse me?
It's like really.
True, but we want. There's also a group structure, which makes it also even nicer. I think that's my last main job for this talk. So briefly, for people who understand this definition, and then I'll flesh it out later as the talk goes on. I need a definition of the packing. It's an infinite collection of round groups to involve whose union extends in Sn. So here I've just stereographically projected R2 onto the unit sphere, and I've drawn my balls. It kind of looks a bit nicer here if you can see it. And the union of the poles represents. And then we call this packing finding. It's a residual set. That is what you get after you remove the interior. Agrees with the limit set of some discrete unit finite subgroup of isomorphy of the hyperquality n plus 1 space. I'll explain what these things mean for people who don't. And here's an example of a tiny packing one dimension up, so it lives inside of dimension 4, but it's in the boundary of 4, which is R3. And again, you get the integral pattern. Integrality of higher dimensions.
So in the previous discussion, you were in the sphere, but you just take out one ball and you have this ball and that ball and have all 6. Is that right?
So in the previous example, this is the boundary of hyperbolic 3.
Oh, I see. That's the boundary.
Okay, so what is the finding or Apollonian accounting of dimension? Well, suppose we have a pure packing dimension. I'm going to let this function b denote the n. And the problem is the following: how many spheres are there with n less than 2? Okay, so we have a quadratic form. We want to count how many solutions to the quadratic form are smaller than t. The last thing you need is group structure, right? That's what I said at the start, that we need this group structure. And the group structure can be arrived at through this nice construction. So I'm going to start with the Descartes initial configuration. I'm going to add in this fourth circle. And I'm going to connect all of the tendency points, or any 3 tendency points, by circles. This gives me what's called the dual cluster. And it turns out that the packing is the orbit of the initial configuration under inversions in these dual. So if I have a circle, you can talk about a certain inversion. I take a point here, you can invert it through the circle, and the point is that this distance will be this distance will be prime. If I remember correctly, OP prime to be the radius squared. So given these 4 circles, you can invert through them, and you should be able to generate the entire pattern. So you can see here that the circle P, if I reflect it through the circle P, I get the circle A.
But OP is the distance, the radius.
The distance from here to here times the distance from here to here should be the radius. So here's our group structure, right? We have, and so we're back into another example of this problem. So the packing is the orbit of the initial configuration under this. If you go back, it's just, so, yeah. Sorry. Well, it's just exactly what it is. Packing into the order. Those are discrete questions. So before moving on, I need some background on hyperbolic n plus 1 states. So hyperbolic is something these are points in R n plus 1, whose last coordinate, so you can think of the upper half. Here's my drawing of hyperbolic 2 space. But we have this volume element. Just one second. We have this volume element where you're dividing by y2 plus 1. So in this case, we divide by y squared, which means that the metric blows up once you get down to the boundary, and the metric goes to 0. Pulls things together once you go up. We have a reminding manifold, so you can define the Laplace manifold, which is given by this hyperbolic proportion, upward sign. It's going to play as you make it a positive operator. I make it a positive operator, but this is contentious. A geometry will be now, given Hn plus 1, we can also define a group of isometries. And at least when n equals 1, then the isometry is given by SL2R acting via modulus. So if I have some point Z, and I have gamma is ABCD, then gamma of C is AB plus B divided by CG. If you move up a dimension, then you get SL2C. If you keep going, then you get some sort of connected component of SO n plus 1, 1. But I didn't want to write those over. It's enough to just work in these dimensions. So if we have a group of isometries, then we can start talking about discrete subgroups. So the image, or the example that I like to think of is drawn over here. This is the group generated by these two elements. What do these do? Well, this one translates you by 3, so it moves you to the right 3. And this one inverts through the unit sphere. Right, so I've glued these two walls together if I'm talking about the quotient space. And that's the same as gluing these two walls together and gluing this to itself. So what you end up with is a hyperbolic manifold. Picking up these pieces of the boundary. So these correspond to these flared funnels. And then I pick up this piece at infinity, but remember that the metric is going to 0. So that's why you get this pinch trust. Okay. If you don't know what geometrically finite and non-elementary mean, it's enough to think about finite generated stuff. Geometrically finite means not too big, and non-elementary means not too small. So if I take this quotient, please get a nice manifold. Some manifolds are compact. So I guess this is my last name, Root Escher. So he worked with Oxford. And what he's doing here is identifying this edge with this edge. It's compact because you're not picking up any pieces of the boundary. In particular, it also has finite volume. Some manifolds have finite volume, but they aren't compact. So here's an example. It's a modular surface. It's SL2 That's my subgroup. And it's not compact because I'm picking up the P17. But it is finite volume because my metric shrinks to 0 as I move up. And then some manifold for this. I'm assuming most of you have seen this stuff before. Everyone likes it.
The previous one was actually Oracle. You could hold full point.
Yeah. Correct. I'd like to sweep that under the rug today. So given a discrete subgroup, I can consider the orbit of a point by this subgroup. So here I take my point C and I orbit it according to the subgroup and it keeps going further. You can see that the points are kind of collecting along the boundary. And so an object that we're going to need, which is called the limits. This is the closure of the set of accumulation points of any order. Doesn't matter which order. So let me just write that down. This is the limit set. And delta gamma for the rest of the talk be the Hausdorff dimension of the limit set. Note that if gamma is a lattice, then the limit set is so dense that, the limit set lattice if it's finite volume. Sorry. So if it's finite volume, then these accumulation points are so dense that the limit set is actually just the whole bound. This is that is finite volume. And if it's infinite volume, then you're going to get some fractal picture. The last thing we're going to need is called the spectrum, and then I can start telling you some theorems. So we have our subgroup, we have our manifold. We can consider the Laplacian acting on this L2 space. It's the Hilbert space and an operator, perfectly nice. The spectrum are all of the real numbers and such that this operator has no inverse. And with the classical picture, at least for discrete geometrically finite nice subgroups, the spectrum is positive, so it's at least bigger than 0. We have a continuous spectrum above n over 2 squared. So all of this space lies in the spectrum. And then you have some discrete eigenvalues here. Below n over 2 squared. That's a result due to and then a result due to Patterson and Stony is that the base eigenvalue, so that's the smallest discrete eigenvalue here, is equal to delta n minus delta, where delta is the Hausdorff dimension of the limit set. So again, when we're in the finite volume case, then the Hausdorff dimension is just n, which means that the base eigenvalue is just 0. Yeah.
Definition of spectrum, I'm a little worried about what that means in my mathematical culture, because delta is an unbounded operator on total space. I don't expect it to ever have an inverse. It's not defined everywhere. I mean, I don't know, what's the actual thing?
So you can't work with L2 space, you need to work with things which are L2 and whose Laplacian, if you act on it by the Laplacian.
No, but let's use the statement. The spectrum is what? It's lambda such that what?
Lambda such that this has no inverse, but instead of working on L2, you need to work on the L2 functions which are closed under applying the Laplacian.
It won't be, this still won't be a map from that sort of thing itself. Change, like function 2 to L2.
Okay, well, that'd be recorded, we don't have that anymore. It's still on.
Now, how do we pass for the spectrum? Well, I've actually already told you how to do this in the Euclidean sense, and it's just Poisson's symmetry. So notice that e to the 2 pi I n is an eigenfunction of the Euclidean function. And so what I'm doing when I apply my Fourier transform is I'm integrating against eigenfunctions. So this allows you to pass from real geometric data to spectral data. In the finite volume hyperbolic space, there's an analog of Poisson summation, which is the Selberg trace. I don't want to write it down because it's very complicated, but again, it tells you how to pass from geometric property to spectrum. The problem is our spectrum is a lot more complicated here because we have continuous spectrum and discrete spectrum. So the trace formula is more complicated. Now, in infinite volume, we don't have an explicit spectral decomposition. But it turns out you don't need an explicit spectral decomposition. You can use this abstract spectral theorem, which is a general theorem about any self-adjoint operator acting on Hilbert space. And what it tells you is there is a spectral measure which is supported on the spectrum. And there's an operator which takes you from L2 on a real of hyperbolic state, Hilbert state, to an L2 space in this spectral world. And it satisfies the properties, and they're really powerful. It satisfies particle type. Tells you that an L2 inner product in hyperbolic world is the same as the L2 inner product on the spectral side of the spectral transforms. Okay? It plays nicely with the Laplacian, namely the spectral transform of the Laplacian applied to P is evaluated at a point lambda is lambda times the spectral transform. And if you have a discrete eigenvalue with eigenfunction E lambda, then we know what the spectral transform is. It's just the inner product of P. And we know what the spectral transform is at that discrete eigenvalue. It's just the inner product of P with this eigenfunction.
Is it in the special case when you're looking at a compact hyperbolic, on the orbital, the story is different, right? There's no continuous spectrum in that case, so we have discrete spectrum.
Yeah, so then you have an atomic measure. It's the same idea that you don't have to. This is applied in general self-adjoint operators acting on the abstract. You can read about this in Brueggem's book on functional analysis. I'm not sure where this. Who to attribute this? And it turns out this is all you need. Okay, let's talk about some applications of spectrum. Talk about the spectrum, and then we talk about how to get to the spectrum. But what's that useful for? Well, the kind of warm-up problem that we talk about is hyperbolic Gaussian or the hyperbolic Gaussian problem. And it states the following. Suppose I have some nice, discrete, geometrically finite, non-elementary subgroup. And I take the orbit of the point C. These are the black points. And now I'm going to place an observer at point W. So here's the orbit of my point Z. And the question is, how many points in the orbit of Z lie at distance C from W? So here I've drawn a hyperbolic circle around W. hyperbolic, which is why it's not centered at W. And the red points are all the points in front of them.
They're not W, but look that way.
It's not Euclidean. Can we estimate the number of points in the orbit which are a distance d from W? Why do we care about this if we're number theorists? Well, if I place my observer and the point which I'm orbiting both at I, then I'm asking how many elements of my group are there? A, B, C, D. Such that A squared plus B squared plus C squared plus D squared is less than 2. Now you might say, why
That's
do we?
for
That's for SLT. Well, no, this is for any group. Yeah. This is in SL2R,
Oh,
but the discrete group
oh,
would be
okay. That's interesting to know.
indeed. So if you take a subgroup of SL2Z, this can be quite nice. Now you might say, why don't we do what Gauss did? Put a ball around every circle, an orbit point, and we'll see what happens. The problem is that our metric is going up now. So in hyperbolic world, a unit neighborhood of the boundary of a circle has the same area as the whole circle. So you would get
All of this.
that's the whole disk. Indeed. So you would get that your count is upper and lower bounded by R, but your error term is also the size of the area of the circle. Okay, instead of working with the eigenvalues, I'm going to define these numbers Sj, which is just the solution to this. Remember, n is fixed. It's just slightly more useful. I can write that down. It'll come up.
Is the dimension.
N is the dimension. Well, we're working in hyperbolic n+1 space. N is the dimension of the boundary. So lambda j is Sj.
So you know lambda j and define Sj by this point?
Yes. So a result of Hoover in the 50s, generalized by Patterson and Silver, generalized it much further, is the following. And it's generalized with all dimensions, but I want to kind of, it gets a little complicated and floating around. The solution to the Gauss circle problem are a collection of name terms which come from discrete eigenvalues, and then an error term of size t to the theta. So the main term has size t in the finite Fourier space, and we also know it is constant.
You said the other suggesting that the 2/3.
No. The 2/3 is the right answer. If you can prove t to the 1/2, which is the suspected answer, then you'd win $1 million because that's equivalent to the hypothesis. So
It might be better. It's equivalent to the minimum.
I think it's better than no, I think it's equivalent.
Okay, but that's not conventionally the short.
Conjecturally, we think it's 2 to the 1/2. But this result is optimal in a sense that I'll describe later. But yes, if anyone for it, you can try and
Also, the other theorem kind of like that. Gauss's theorem was about 2/3 too. So
and
0.61.
yeah, there's reasons. We'll get into it once we talk about the method. And now back Phillips. So these guys were all using versions of the equation. You can recover all of this using the equation. But Lax and Phillips said, hey, you don't actually need this explicit spectral decomposition. It's enough to know a little bit about the spectrum. And you get the same kind of theorem. You get the same main terms coming from discrete eigenvalues. And then we get an error term which is the same, but now it incorporates this house of dimension. And again, this is optimal in the same sense as the last theorem. So optimal, which I'll tell you at the end. And here the dominant term is G. Okay. And again, delta is the Hausdorff dimension of things. And it's also, because of this formula, delta is at 0. Right? These are the same formulas.
These other essays were from generalization of the house.
Here they come from something which is called a Patterson-Sullivan distribution, which is not a Patterson, which I haven't really looked into, but
He's not alone.
I'll let you have it.
It would be nice if all these eigenvalues enter into the S language at the same time as geometric description of house.
Yeah, I don't think there's a nice geometric description like that. At least not the one. And this generalizes all dimensions. Again, it just gets more complicated when you write it. Okay. One slight modification of this problem is what if your observer is anything? In which case you're counting points that lie above a line. This is meaningless if your line extends everywhere. So we need a mod out by the stabilizer. So we're only going to count points in the strip. And now you're counting c squared plus d squared less c. Whereas before we were counting a squared plus b squared plus c squared plus d squared. So a theorem of Kontorovich generalized on myself in Kontorovich is you get the same kind of asymptotic. You get main terms coming from discrete eigenvalues and you get an error. This error term, while it looks different from the previous ones, it's optimal in the same kind of way.
Well, what is K?
K is just the number of discrete eigenvalues. Plus 1. K plus 1 is the number of discrete eigenvalues.
There's a finite number.
There's always a finite number.
If you're setting the
geometrically finite, I think gives you finite and then discrete eigenvalues below n over 2. So.
Okay, that's low and over.
Low n over 2. So you can have embedded as well, but not in infinite volume.
The one below some number depending on the dimension. And over 2 squared.
So in infinite volume, it's just the total number of discrete eigenvalues. In finite volume, you can get embedded eigenvalues, so then I'm just talking about below the continuous sector. This is
Part of the empty part.
This is not
Visible eigenvalues.
the visible eigenvalues. And for example, if you're a number theorist and you want to count Pythagorean triples with size less than t, then this asymptotic property. This was done by Kontorovich and O, but they get a much worse error term using redistribution and power spheres. But using the spectral method, you can get an error term again in some sense.
Which one's better? The same or?
But is that just Euclidean norm of rebounding, or is it the largest? Or you have to permutations?
I think it's the same thing. It would be the same asymptotic. But so Okay, what does this have to do with finding packing? So I told you about this group structure. I don't know if you can really see. I told you about this group structure that I have these dual configurations, which the orbit of the initial configuration under the dual cluster gives you the packing. Well, I can embed the dual cluster group generators in the boundary hyperbolic free space. That's what I've done. And then on each of those, I can trace a geodesic chemistry. So it turns out that this group, which generates my finding packing, is a subgroup of the isometry. And this is how I define the finding packing, but it turns out this is proof of Apollonian. And it also turns out that the Apollonian packing is the limit set of under this group. And this is what I've drawn here. This is not a fake picture, this is actually a given point. And I orbited it by a group generated by these four reflections.
This is a point in the interior hyperbolic space.
This is a point above the plane, and I think it's orbit, and bounce back and forth. And you can see that they're collecting here on what's starting to look like an Apollonian pattern. So it turns out that we're living inside of hyperbolic 3 space for the Apollonian and hyperbolic n+1 space for the Okay, we have a specific group, the Apollonian group. Now I'm only talking about Apollonian. So what do we know about its spectrum? Well, thanks to Max Phillips, actually Sullivan, we have this continuous spectrum above here. There are some discrete eigenvalues. And the smallest of these discrete eigenvalues is written by delta. So delta, where delta is the Hausdorff dimension.
When you say the Apollonian group, you say abstractly it's the same group.
It's the same for all Apollonian packages, so it doesn't matter what initial configuration you start with. But there are Kleinian packages which are not Apollonian. So now I'm only focused on them.
But for different Apollonian packages, they actually have different representations of the group.
They're all conforming to so they're involved by some element of SL2, SL2C, and you get that. We actually know what this Hausdorff dimension is. I won't point to you. I believe McMullen had the record. I think this is recently completed by a student of ours, Pontorovich, whose name is Alex Karlovitz. But okay, we have a very good estimate. All of these significantly were verified, and I think it's verified for about 30 years. So that tells us what this base eigenvalue is. There's a conjecture of Sarnak that there are no eigenvalues other than those. So all of these things there.
Only one there.
Supposedly there's only the bottom. And I'm pleased to be able to say this is no longer a conjecture. So together with Stephen Helmer and Brook, we were able to prove some group. So, in fact, we understand a lot about the spectrum. There's a discrete eigenvalue. We know what it is, up to 60 digits, whatever. And then there's the continuous. And that's it.
Does this prove Riemann class?
This does not prove. I wouldn't be speaking here. If it did, I'd be at home writing.
The formula that you had before, you call it simplifies.
It does. Well, I haven't presented you the formula for the Apollonian results. But here's the formula for that. Together with Alex Rodich, the answer to the Kleinian pattern problem, assuming no other eigenvalue other than this isn't always true, but it is true for the Apollonian. It's given by T delta, and then this error. This error term is optimal, And as Bennett pointed out, we can avoid the contributions from the other eigenvalues because we know they have that. Otherwise, this would get worse.
Well, let's say that.
Eta is a delta. So it was this and now. So it improves by an order of magnitude.
But that second term is bigger than.
But it's delta minus.
Oh. Oh, yeah. Real small.
And this improves on some work by Boyd and and it's again optimal in the sense which is going to come clear in a couple of steps. All right, so I'm going to go back to this problem where I count points above where I count points above some cutoff. Because this will give you some of the ideas that go into the proof of the outcome. I don't want to go into it. So this is our counting function. So counting the number of group elements, we have to get rid of the stabilizer at infinity, otherwise this is meaningless. And we want c squared plus c squared to be less. So what we're going to do is the same thing that the book did. We're going to create a monthly function. And now we're just going to sum over the group elements, whether or not this is a data function. The next step is the same. We're going to smooth our count. So we're going to define psi epsilon to be an epsilon and half. We're going to automorphize it, which is averaging over the group. And then the way to smooth hyperbolic function in a nice way is to take the inner product with this qualifying. And what this essentially does is it creates these little epsilon bumps around the points. So now instead of having Dirac masses, we have epsilon bumps. And now the proof is kind of simple if I brush aside all of the complicated part. Which is, I have an L2 mirror product on this L2 space, so I can apply particle lightning. I can pass to the spectral side. Even though I don't know anything about the spectral side, I can pass to that spectral side using the abstract. We can pull out all the discrete eigenvalues because I told you that the spectral measures lives on the spectrum. So we pull out the discrete eigenvalues and we get this term, which lives on the spectrum without the discrete eigenvalues.
Spectral measure I do in processing
Now it takes you from a Hilbert space, to the spectrum.
Oh, that's
yeah. Well, I told. So this is talking about moving.
Oh, this abstract property. Oh, we said it already. Okay, I understand.
So I pull out the contribution to the discrete spectrum, and I get this error term. But now remember that the contribution to the discrete spectrum is just the inner product with the eigenfunction. So I know what all of these terms are. They're t to the delta, or t to the s, and then there's some constant, which depends on epsilon. And then this is where the sort of meat of the proof comes in. That's making we get t to the 1/2 log t, 1 over epsilon.
After the log.
Well, this is optimal. This is optimal. The problem is the reason this isn't the Riemann hypothesis is the epsilon. Because this epsilon fights with these epsilon.
Oh, the epsilon.
So we're optimal if we're counting smoothly, and this is what I meant when I said Selberg was optimal. He's optimal if you smooth, and lax Phillips are optimal if you smooth.
So Newman is true if it's, Gauss is true if it's true.
Yeah. Yeah, I think if you smooth, you can recover Gauss's. Maybe up to some level. So when I said optimal, this is what I meant. For fixed epsilon, this is optimal. But now we need to optimize because these guys grow with epsilon. These guys shrink with epsilon, but these guys contain terms that shrink with epsilon, and these guys blow up with epsilon. So you need to pick the right epsilon and stop. And then you get the theorem. And then we know for the Apollonian case that means that there's no spectrum other than. And that's all I have to say. Some credit goes to Alex for drawing.
Are there any questions?